Hi, I would like to present Oracle AutoML, a fast and predictive AutoML pipeline. This was work done at Oracle Labs, and Oracle AutoML is currently available to customers in Oracle Cloud Data Science Service. This is a required statement. First, I would like to motivate why we had to build our own AutoML pipeline, followed by presentation of Oracle AutoML, a fast and predictive AutoML pipeline. Then I'll present results and comparison with AutoScaLearn and open source H2O, which are two popular alternatives. Finally, I'll summarize with some conclusion remarks. There has been explosive data growth, which requires fast-paced develop and deploy model lifecycles. AutoML simplifies ML productization in cloud applications for a wide variety of users, starting from a novice and all the way to experienced data scientists. Existing AutoML solutions have certain limitations. For instance, they're not optimized for efficiency, delivering lower performance per dollar to end customers. Also, they're not fully automated, which makes it harder, especially for a novice user, to actually utilize these services. Oracle AutoML is an iteration-free AutoML pipeline and is designed to solve these industry challenges. It produces tuned models which are better or at least on par with the existing solutions, but it does so much faster. We're able to achieve 3.5 to 4x faster than alternatives with better results and more accurate and robust models. Oracle AutoML leverages early algorithm selection early in the pipeline, which allows us to use selected algorithm to do model-dependent adaptive data reduction consisting of adaptive data sampling and feature selection. The data reduction reduces the data set size so we can perform faster hyperparameter optimization. All of this is possible due to our use of metalearned proxy models, which are used at every pipeline stage to make accurate one-shot decisions. What are proxy models? A proxy model is a machine learning model that is indicative of performance of a tuned algorithm on a given data set without actually performing tuning. We use proxy models in all stages of Oracle AutoML, including in algorithm selection, adaptive data reduction, and hyperparameter optimization. The benefits of using proxy models is that it allows us to decouple different stages of a machine learning pipeline, which enables for fast and efficient iteration-free optimizations. To get the proxy models, we meta-learn these hyperparameters for the models on a diverse set of OpenML datasets. First, we generate a wide variety of representative hyperparameter variations per algorithm, which are a combination of randomly selected and default values. We then evaluate performance of every configuration on all algorithms on a wide variety of data sets and heuristically identify the best configuration per algorithm that performs best across all the training data sets. This approach allows us to get proxy models that generalize well to new and unseen data sets. For algorithm selection, we're able to put it early in the pipeline stage because we rely on proxy models to select and rank the algorithms. The goal of algorithm selection is, of course, to select the best performing algorithm for the given data set and use it throughout the rest of the pipeline. We first subsample the data set to reduce the number of rows to speed up evaluation. We train and evaluate all the proxy models, which represent their corresponding algorithms, and select the highest ranking algorithm. Once the algorithm is selected, we can actually use model-dependent row sampling and feature selection. The goal is to reduce the number of rows and number of features to only keep the representative set. Data reduction cannot degrade the score. And again, we utilize proxy models to evaluate different subsets of the data sets. For row sampling, we select the smallest sample size that doesn't degrade the score, and we balance data across classes to mitigate data imbalance. Feature selection ranks and evaluates exponentially growing feature subsets and select the smallest subset which doesn't reduce the score. Finally, once we reduce the data set size, we can do hyperparameter optimization much faster. The goal of hyperparameter optimization is to quickly identify good enough hyperparameter values for a given algorithm. And we also try to maximize available parallelism and forward progress by mitigating stragglers. Our approach searches along each hyperparameter dimension independently, and we eagerly and asynchronously combine these results. It consists of two stages. The first stage quickly narrows down the search space, reducing it to much smaller subset of search space. And then we finally fine-tune using gradient descent. We leverage batching of hyperparameters to mitigate stragglers. We bootstrap our search using proxy model hyperparameters. And we utilize training time prediction to avoid expensive trials. And as I mentioned before, we do asynchronous and eager result updates to make sure that we only train across the best hyperparameter values. To evaluate our pipeline, we selected 30 diverse test data sets of various sizes, as can be seen in the figure on the right. For every data set, we do the 80-20 train test split, which is common in the industry. And we repeat every experiment 5 times with different random seeds. The optimization objective is to minimize log loss. To evaluate, first of all, we try to compare results with open source H2O and AutoScaLearn, which are popular alternatives according to the industry, customers, as well as literature. We also try to measure efficiency, which is how fast pipelines can produce results, and they have to be accurate results, and also robustness. That is, the pipelines have to produce models even with short time budgets and even on large data sets. First, we show a ranking of the pipelines for different time budgets. For this, we provided different time budgets starting from 1 minute and all the way to 60 minutes to every pipeline. And we plot the ranking across the 30 different data sets and 5 random seeds. As you can see, Oracle AutoML significantly outperforms and outranks its competition, starting from the smallest time budgets all the way to the largest time budgets. The lower rank, of course, is better. And it's worth noting that AutoScaLearn and the H2O fail to produce a trained model for shorter time budgets for some of the data sets, as can be seen from the table on the bottom right, which shows percentage of trials that produce the tuned models. Oracle AutoML is consistently producing a trained model for every time budget for all data sets, which makes it more accurate, more faster, and more robust. Now I would like to show the leave-out scores on 30 data sets with a 60-minute fixed time budget across 5 different seeds. The plotted score is log loss error, and lower is better. As you can see, Oracle AutoML achieves significant lower average log loss than competition. Additionally, Oracle models have tighter log loss distribution, which means the results are more consistent throughout trials. And importantly, Oracle AutoML completes optimization across 30 data sets 3.5 times faster than H2O and 4.1 times faster than AutoScaLearn. To conclude, Oracle AutoML was designed to address the industry challenges by producing highly accurate models fast. This is possible due to unique iteration-free pipeline design, which leverages accurate early algorithm selection stage. This is possible due to relying on metalearned proxy models to make these accurate decisions. Fast results benefit wide spectrum of users, starting from a novice and all the way to experienced data scientists. And this is crucial for vast adoption of machine learning technology in cloud infrastructure and applications. Oracle AutoML is available to customers in Oracle Cloud Data Science Service. We hope you can read our paper, which is number 831, for more details on implementation and extensive results. Thank you very much.